Hi, so good evening, everyone. Um, Welcome to the stream. Tonight, what I'm gonna be talking about and presenting is first talk a bit about OpenLANE. Um, so we're gonna talk about the Sky130 PDK to make ASICs. And more specifically, updates about what I talked about on the last stream. And the main thing is going to be the release of OpenLANE. And then I want to explore a little bit the Python bindings for OpenDB, which allow to kind of manipulate programmatically the like the design objects, basically. Um, Hi, good evening, Cryptalist. Um, so yeah, let's just get right to it. So the first thing is OpenLANE. So OpenLANE is the name that's been given to the essentially the entire flow, where you just give it some Verilog design that you want to implement, and it will perform all the steps to go from that Verilog description to literally the GDS, which is like the product for tape out. At the moment, sorry, it doesn't do the entire chip itself. It only does macros, so kind of a hard block that you would be using inside a chip. But that's just because the I/O libraries, all the way to interface the chip to the outside world have not been published yet. So at the moment, they can't support that. Um, so we're just gonna take a quick look about how it works. The repository is on efabless OpenLANE. You do need to check out the RC2 tag, which is the latest stable release, because if you try running stuff off master, it's not guaranteed to work, or there will be broken things and stuff like that. So you really want to stick to other release tags, and you also want to follow the installation instruction here that will tell you also which exact version of the PDK you need to check out. Here they give you the exact git hash you need to check out. Here you need to take the RC2 tag of that repository. You need to follow that exactly, else you're gonna have a bad time. I mean, you can experiment if you want, but following the instruction will make it easier. By default, it does run in Docker. That's what they suggest. Um, because I don't really like Docker, I did build everything natively, and I actually published the script that I used to do that. So I wrote a repository that's called OpenLANE bare metal, where you have a build script here that will basically take all the tools, all the repository, and build them like in a given prefix on your machine natively. And again, like the important thing here is that it goes and check out specific hash or specific branches of all the tools, because that's the components that are known to work together and produce valid results. It's not always the case if you update some of these tools. So that's mostly what this script does, is basically install everything and check out the right version. Also, a lot of these tools, I think, are written by electrical engineer rather than computer engineer, or maybe that's just my view of it. But like they will build fine and they work fine, but the make install target for most of them is absolutely horrible. And so most of the time you just end up copying the resulting binary, because if you do make install, it will install tons of stuff at various places that it shouldn't and stuff like that. So yeah, for all of these, don't trust the make install. So how does OpenLANE, what does OpenLANE look like? So just gonna go to the workspace I installed it in. So because I do everything in a prefix, I need to set up my environment. And this will define all the environmental variable like the path and stuff like that. And also where to find the PDK, that kind of stuff. Also, you might want to be careful. I didn't have enough space on my temp directory by default, and the flow does create some very large temporary file. So I put the temp dir somewhere where there is actually space. So now this is OpenLANE itself here. So you just do a checkout of OpenLANE. The main entry point is flow.tcl, and if you look at the README, if you just want to run a design, you just call flow.tcl, tell him which design you want to run, and it will build it. And so you have different options. So we're just gonna do that. We're first gonna have a look at the design itself. So the first design they recommend is SPM. I honestly have no idea what it does. So you have the Verilog source. It's like a single source file, so it's pretty easy. And so you have here a very small design that does something with 32 bits. I'm not entirely sure what. Has anybody checked out what this does? I didn't. I never look. It's like a comparator and an adder or something, but I'm not entirely sure. Anyway, so it's some Verilog source, the ones that you want to build an ASIC for. Then you have like a constraint file that will say, okay, I want to run that design at 100 megahertz, so period 10 nanoseconds, right? So you want to run it at 100 megahertz. Then you have a few configuration file. It's interesting. I don't remember what config.json is. You can set some parameters for the design. All of these are explained in the OpenLANE README. Most of the time, you really don't have to change them compared to the default. One thing I'm gonna do here is actually change the routing strategy. I'm gonna set the routing strategy to 14. So this routing strategy 14 is gonna use a different router that works better. It's newer, so I'm just gonna use that one. So let's just run that design. So we just call flow.tcl. We say that we want to synthesize the design SPM, and well, let's just do that. I'm gonna time that, and it will start doing its thing. So if you're used to, well, that's a bad start. What? Okay, so it's not supposed to do that, right? What? Of course, I tried that, right before the stream, and it worked fine. Yeah, what's the problem with? This is just Perl is throwing some error, and it gets interpreted as an error. For fuck's sake, I hate this shit. setting local failed. Okay, why? Does it do the same thing here? Yes. So obviously I screwed something in my install recently, or okay, let's just do that and restart. That's unrelated to OpenLANE. That's my system being screwed up or whatever. So as you saw, it just ran uses, but it just goes too fast to really see anything. And then it will do a bunch of different things. We're gonna look at the output of each stage so that you can see exactly what kind of what it does basically. So I was also saying if you use to like the ICE40 flow or the ECP5 flow, that kind of stuff, it can be slower. Like currently trying to run like a vex-based design, like a RISC-V implementation or something like this, you're looking at 30 minutes to an hour of build time, right? So yeah, that's not especially snappy. So this one is just gonna take a minute. Yeah, it's almost done. That's the last step. So running antenna checks. There you go. So it took like a minute and 42 seconds to build. But it's, as you saw, the Verilog file is very small. Right? That's like a few 32 bits adders. So that's like a really small design. It still took like a minute, right? That's the equivalent of a Blinky or something. So we can take a look at the different outputs of this. So let me go here. Main workspace, then design, SPM, results, no runs. So it will create a run directory for every time you launch it. So this is the latest run I attempted. By default, it's the date, but you can override it and set whatever you want. But yeah. So if you look in the results, so the first step it will do is synthesis, and that basically takes your netlist and converts it to a list of cell libraries. So that's that's a flip flop, for instance, and that kind of stuff. And so they all UOSIS and ABC will convert your like RTL Verilog into a list of cells and how they are interconnected. An interesting report for this that's done during synthesis is the STA, so the static timing analysis that you can find in a report synthesis. That's the the post-synthesis STA, basically. So it doesn't account for layout or anything like that. It uses estimated wiring delay, basically. But here you can start to see, I'm not actually sure if there is, so it will do a min and max analysis. So that's the minimum delay, and that's used for verifying hold time, so that the data doesn't change too fast, so that the flip-flop works properly. So each flip-flop has a hold and a setup time, and you use the minimum delay to check the hold time. And so here you see that's the minimum between two flip-flops triggered by the rising edge of the clock. And so you have the clock changing, and then the data will change 0.9. At minimum, the data will change 0.9 nanoseconds after. So that's 900 picoseconds after. And the library has a required hold time of minus 0.1. So it has actually a negative hold time, which is great. And so we have 1 nanosecond of slack. So there's no problem. It meets the hold time requirement. And then we can look at the setup time requirement, which is computed using the maximum delay. Do we have a flip-flop to flip-flop path? No, it looks like the maximum path is this one. And so again, you have the maximum delay. So here, it's not actually from an internal flip-flop to an internal flip-flop. It's from an input port that's considered to be clocked by vclock. It's not super valid like as analysis, because that delay is like completely arbitrary. 2 nanoseconds, it comes from nowhere. It's just completely invented. So not super happy with that. I'd have to tweak that. But you can start to see the kind of delay that the gates take. Basically, you see, to go through 1, 2, 3, 4, 5, 6. To go to 6 gates, it basically took 530 picoseconds, right? So that would run really, really fast, basically. And again, the flip-flop has a required setup time of, where is it? There's a required setup time of minus 0.008. Okay. That's interesting. So the fact that the hold time and the setup time are negative are a bit surprising. I mean, there is a gap between the two of 0.02, but that means there is only a gap of like 20 picoseconds between the hold time requirement and the setup time requirement. Between the required data valid window is like super small, which is interesting. Anyway, we meet the timing like by a massively huge margin, right? So there is no trouble there. Currently, OpenLANE doesn't have the post place and route timing analysis, so that will come later. We can open some of the, yeah, I can start that. Let me see if I have reader option, technology, Sky130. Open a new panel. And SPM runs this one, results. So I think the first thing it does after synthesis is the floor planning. And so that's what the design looks like after the floor planning step, is that you basically, the cells aren't placed yet, they're nowhere to be found, but it already like decided of the general area of the chip and where the pins are gonna go. Like because this synthesizes like odd macros, all the I/O are spread around the chip, and it also placed some of the special cells. These are decoupling capacitor basically between the power rails. If you look the cell type, they're called decap. These cells, that's a decoupling capacitor. just like on any board, except those are on chip. And then you have these, which are the taps, and these are to prevent latch up. Basically, it's to bias, to properly bias the bulk, so the P substrate of your chip, and the N wells. So if you remember last stream, we looked at the different layer, and so you need to bias them to prevent latch up, and that needs to be done like regularly on the surface. The PDK, the DRC rules, the design rules here, I don't remember exactly where, but they specify that there is a maximum distance between any transistors and one of those special tap cell that biases things properly for things to work. And so here, the first step is distributing them like on the chip, basically. Now, if we open the next step, so after floor planning comes placement, I think. And so here it actually places all the cells. Let me, okay. So all the cells have been placed. I don't know if I can show just the, yeah. It's a little clearer if you don't see all the layers. And all the cells are placed on a grid, basically. So you saw there was a bunch of rows, and here it decided, okay, where do I place each cell, so that they don't conflict with the tap cell and all that kind of stuff. But at this point, there's still no connection, right? It's just the placing step. So the next step is routing. So if you close this, look at the next step, which is routing. Here, you have your design, and it's completely, even if I only show the, don't show the internals of the cell, you can see all the metal connection here, all the vias and stuff like that. You know, this is all the metal layers interconnecting all the cells, and also providing all the power. So for instance, if you look at, let me just idle the layer, metal 5, metal 4. So that's metal 5 and metal 4 layers. So in case you don't know, on the chip, things are routed like in a kind of old PCB, where you have one layer which is routed all the horizontal connection, then another all the vertical connection, and then all of that, all like that. And so here, metal 5 is an horizontal routing layer. Metal 4 is a vertical routing layer. Metal 3 is going to be another horizontal layer. Metal 2 is going to be another vertical layer. That kind of stuff, right? It's the preferred routing direction. And metal 4 and metal 5 here are only used for power distribution. And so you can actually see that wait, where's, there should be vias between them. Oh yeah, but you don't see them here. Yeah, here. So you see that this rail is connected to this rail through this via, because that's probably, I don't know, either GND or VCC, and then you have got this rail which is connected to that rail. Again, we have this via. Here, of course, there is not many rails and not many interconnection because the design is like super small, right? But you have to imagine that your chip, I mean, this is 100 micrometers pretty much. The entire chip is gonna be, you know, like 4mm by 4mm. So, you know, it'd be something like this, right? So you have an entire grid distributing the power all across the chip. to make sure that you have a low inductance path for all your power connection, basically. Let me reshow all the layers. And here you can actually very well see the all the rows of standard cell, which are distributed in rows, and their orientation varies, right? Because this rail is gonna be I don't know if that one is VCC or okay. So this one is VCC, and then this one is ground, and then this one is VCC, and then this one is ground, and that alternates like that. And so they just flip the standard cell horizontally depending on which row they are placed at. That's something it's going to be useful later on in the stream when we try to actually place our own cell and connect them and stuff like that. So here I open the def file. So the def file doesn't have actually all the detail, but you can open the final kind of tape out file, which is the GDS, and that's gonna be in Magic. Here you have the GDS, and that has all the layers, all the details. You can basically fab the chip with that, right? That has absolutely yeah, everything you need, nothing hidden in there. So that was kind of a quick run of OpenLANE. Of course, you can create your own design with OpenLANE, right? You're not limited to just running the examples. And they have, let me find, what is this? Yeah, that's the thing. So if you wanted to create your own design, you can just use the same utility. Let's say I want to call it test, and then init design config, and that actually creates the directory, the source directory, and a base config.tcl, which you can modify depending on your needs. And then in SRC, you can just include all your source files. So let's say module test input wire 31a. My keyboard is not in a super convenient place, so I do a lot of errors. Sorry about that. So that should be a PDM modulator, if I'm correct. Do you think I'm gonna get it without syntax error on the first go? So let's try to run that design. Yes, no syntax error. Amazing. So it's going to take a few minutes to run through the design, and then we can have a look at what it actually did output. Hi there, everyone. Zeus and Rombic. It's funny. So as you can see, even for a very simple design, it can take a lot of time. Now, a bunch of the steps you can actually skip. If you want to iterate and just see some results, you can actually skip a bunch of steps because some of the steps that take the most time are kind of DRC checking and stuff like that. Oh, hi, Peter. Like this is like the X thing and antenna check. So X is extraction. So it's basically analyzes the design and extracts the parasitic. So how much capacitance does this node have and stuff like that to be able to do more accurate timing analysis. The antenna check, it's a special check to verify that you don't have any so-called antenna on your design. So in case you haven't seen that, there you go, the antenna effect. And basically what happens, what can happen is that your chip is supposed to look like that, right? But while you're building it layer by layer, and so you can actually have the gates of some transistors, which in the middle of the production, that gate isn't actually connected to anything, and so it's susceptible to collect if there is a large plane of metal or wire of metal connected to it. It can collect like electric charges and basically creates like a small sort of ESD event where you basically destroy the gate oxide of your transistor before you've finished building it, basically. And so there are special precautions that you need to take to deal with that. Wow, yeah, it takes just the synthesis takes 10 times. Yeah, that's really not surprising. I mean, especially if you want, good mapping to your gate library. I think the current option, even with the flow that we have here, I think the options that are given to users are more optimized toward time than real good results. But if you want an antenna to call home, well, yeah, it's actually badly named because although it's called antenna, it's not antenna as in an electromagnetic field receiving. It's um, electric charge, yeah, static charge. Yeah, it's a more formally plasma-induced gate oxide damage. Okay, sure. And so currently in here they actually explain several strategy to fix this. In OpenLANE, the current strategy is to always add a diode, basically, like every time, all the time, which isn't optimal. The next step is to always add a diode, and then if that antenna, if that diode isn't needed, then you remove it. And you still have a gap at that spot in the chip, so it did use space for nothing. But removing the antenna, removing the antenna diode helps lower the capacitance of that wire, basically, because that adds a small capacitance which slows things down, right? Yeah, I mean, I think for showing how OpenLANE works, that's pretty much all I had to say. Yeah, here you have the flow actually explained. So that's kind of the goal. Not everything is there yet because like DFT doesn't exist at the moment, and the RC extraction and the post routing static timing analysis is also non-existent at the moment. In the published flow, right? They apparently have some things working already, but it's not in the currently published RC2 release. Okay, so I'm gonna move on to the next thing I wanted to talk about, and that's implementing a register file. So imagine that, you know, crazy idea, you want to implement a RISC-V. You're going to need somewhere to store your registers, right? And you basically have two choices for that. I mean, the two obvious choices, rather, yeah, there are more choices, of course, but the two obvious one is first, you can use a bit of SRAM, like a memory macro on the ASIC. And typically, you know, FPGA, if you look at the how the register file would be implemented, it would use either a small distributed RAM or like in the ICE40 or the ECP5, you're gonna find a block RAM used for the register file. And so here we could use an OpenRAM macro and implement the register file that way, right? There is a couple of issues with that. The first one is in your register file, what you want is, at least for kind of common RISC-V design, I would say, is you want two read ports so that you can read the two register arguments at the same time in the same cycle, so you don't lose cycle just to read arguments out of it. And you need one write port to write back the results. And those three ports need to be independent. That's currently not something that's supported in OpenRAM, and that's also something that wouldn't be supported given the SRAM cells that are available for Sky130. They haven't been published yet, but that's my understanding of the cells that will be provided by the foundry wouldn't support this kind of three-port configuration, basically. So the way you'd basically implement that anyway using only two port is you replicate the RAM, right? Because like even in a FPGA you don't have three port in memory. I don't know any FPGA that has that. And so what you end up implementing is basically you have your write port, and then you have your read port 0 and your read port 1, and you write the same data to two RAMs at the same time. And so you could do the same thing on an ASIC, right? But of course, that would take twice as much area. That's the first option. The other downside of using OpenRAM for a register file is that my understanding of the way it works, I don't. Let me see if I can find a quote that made me think that. Oh, Yeah, I'm not sure where I'm gonna find that code, but basically my understanding was that during a read cycle, OpenRAM used the higher. So if that's your clock, the high part of the clock cycle was used to precharge the bit line. Wait, let me change this. And then the actual read was done in this part, which means your clock to out if you take your clock to out from the rising edge, basically you were losing half the cycle all the time because of the pre-charge time, and then you had the clock to out of the read that was starting here and going there. And that meant that the total clock to out of that macro was actually rather large, which is not necessarily ideal for a register file, because that means you have a 2-cycle latency for your read, because you'd basically have to put a register here basically again, which isn't, adds one pipelining level, which, if you have a pipeline flush because of a missed branch or something, that's one more cycle latency and stuff like that. So yeah, that's the other reason that made me think that using OpenRAM for a register file might not be ideal. Of course, it's entirely possible that I completely misunderstood this and that I'm wrong there, right? But there's still the first reason anyway. So the other option is to, if you don't have a RAM, you can actually let users implement the RAM as flip-flops. Yeah, that's the what I'm talking now. It's yeah, you can just let users, and it will. That's what actually, if you do it now with the current flow, that's what it will do. Of course, that's a lot of flip-flops, because what's the design we're working on at the moment, as it's a classic RISC-V, so you have 32 registers, 32 bits, and ideally I'd like a shadow register set for quick swap between interrupts and non-interrupt context, and that's 8,000 flip-flops. The entire VEX itself, like the CPU core itself, is like about 2,000 flip-flops. So we have 4 times more flip-flops for the register files than we have for the entire CPU. So that's fairly significant part of the area, right? And if you look at, let me open PDKs. DFXTP. That's you know what? That's not as bad as I thought, but still, that's the size of flip-flop. right? You can count the transistors. You have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You have 24 flip-flops. I mean, like a classic SRAM cell would have 8 transistors. And here you have 24 of them. So you can imagine the area of a SRAM cell compared to the area of a flip-flop. This is much bigger. So the downside of letting users do it is, first, it's much bigger, and also if you let the tool do it entirely automatically, it can have difficulty routing, because it will just distribute things not entirely randomly, but it's not necessarily aware of the very repetitive structure of a register file and way to create it in a neat array that is easily routed and stuff like that. And it will kind of distribute it sort of organically, a little like it wanted. That's not necessarily optimal. And so what I wanted to do is to basically use a Python script. Well, two things. First, concerning the regular structure, is to use a Python script to manipulate the design to manually arrange the flip-flop in a structure that makes sense inside the design itself. And secondly, is instead of using flip-flops, is to use alpha flip-flop, which is basically a latch. So if we compare, I expect the latch to be smaller. I hope that I'm not gonna make a fool of myself, but yeah, it is. It's not quite twice as small. If we measure, can we measure this? Yeah, that's useless. Okay, so that's 552. That's 7.36. So yeah, it's definitely not alpha flip-flop. Oh yeah, I'm sure that that ARM definitely has pre-made macros for common process. Yeah, definitely. I mean, the foundry probably can license it to you without you ever talking to ARM. I mean, that's kind of what eFabless does, right? I mean, eFabless has a you can just drop an ARM core there, and that's already validated for that design and stuff like that. So, and you never have to talk to ARM. Yeah, exactly. So yeah, this is 550. So the height of the cell is. Oh my God, I'm an idiot. I've just realized that I don't have the correct screen displayed. So yeah, I was talking. That's a flip flop, right? I've loaded it from the standard cell library, and this, if you compare it to a latch here, the latch is smaller, right? It's the length of the latch here is 552. Let me, can I suppress that? Never mind. The length is 552 here and 736 here. So and the height is common between the two. Like the height is always common in the standard cell library. So by using latches, we can win some area. And how many? 1, 2, 3, 4, 5, 6, 7, 8, 9. So this has 18 transistors compared to 24 for the other. I'm not sure if there is a smaller latch. So that's DLXTP. Not sure if DLXTN is smaller or not. It doesn't look like it. It looks to be exactly the same. I don't know why I can't. Yeah, 552, 552. So yeah, it's the exact same width. So the idea would be to basically design a register file using latches manually. So how would that look like? Let me switch back to this. Sort of first thing is latching the. So let me draw a timing diagram of the so you have the write address and then you have the write data. And the clock. Look something like this. Yeah, sorry, it takes me a little bit of time to draw that up, but okay. So write address 0, write data 0, write address 1, write data 1. And so this is the point where the write happens. Write 0 is triggered and write 1 is triggered here. So first thing we're gonna need to do is latch write data, write the latch the write address and the write data. So these are not flip-flop, they're latches. So I put enable and not a clock line. And we want to let the data through during the low part of the clock. Can you see my cursor? Yeah. So basically during this part of the clock cycle, I'm just trying to think how this thing is gonna work. Wait, no. Yeah, sorry, I need to think. I tried to think a little bit before, but now that I'm reseeing the diagram, yeah, I think that's correct. So during the low clock cycle, we let it through, and then we actually no, yeah, that's correct. So that means that when the clock here rises at this point, the data, the output of these two things is going to be stable for a little while, basically. And that's during this part here that we can actually, these are just to stabilize the input, basically. They just capture the input, and then and we do that during this half cycle, and then during this half cycle, we're gonna actually take the stable data and write it in one of our 64 latches. I mean, we have 64 latches per bit. Like, if we have a 64 by 32 bit memory. And so here we're gonna have a bunch of latches, 64 to be precise. And we have how many bits of address? 6 bits of address that we decode into 64 enable lines. And then we have a clock gating here. And then we have something like this. So during the low part here, the write address just goes through transparently, starts flipping all the enable line and prepare everything. And so here the signal is becoming one only for the one in 64 register, in one of 64 latches that we want to write. But it's not actually writing because at that moment the clock is low, which means that this AND gate outputs a 0 and the latch is stable. And then when the clock becomes 1, this stays stable because this latch is now closed, and so data isn't going through, and this stays stable. And this becomes 1, then this becomes 1, and the latch here will start storing the new value that we captured through this latch here. So that's the write circuit, which I think works. Now, it'd be nice to be able to simulate that. Unfortunately, I had a look at the simulation models. So if you look in the PDK, PDK, SkyWater PDK, libraries, SCHD, latest models. So like if I want to use the DLTP latch, No, the LXTP, sorry. So there's a bunch of models, right? But oh wait, no, that one actually might work. Does it? I looked at some of these DLXTN. It's interesting. What did I look at? I was okay. So if I look at this one, right, which is pretty much what I'd want to simulate. Yeah, no, there's some weird things because like this delayed signal, like it's connected to nothing. Like there's so I'm not sure. Yeah. So if you look at the I mean they're not Verilog models. These are the just JSON containing the timing data, and they generate Liberty a timing file for that. But you have the different corners. I mean, you don't have all the corners. You only have SS and FF. You don't have SF and FS. But you do have the typical and the slow and fast. Um, but you don't have Verilog models that use the timing information. Like none of the Verilog model delay, and that's why I'm not sure I can actually use them to simulate this, because like a latch, I mean two latch following each other, you need to simulate the delay, because else I think the simulation is just not gonna work, right? Because yeah, you kind of count on the small delay for things to work basically. But that's something I could manually add myself, like slightly delay the clock of one of the um, latch for simulation or something like that. Um, but yeah, because this includes this, which at least exists. That's something I didn't even know existed in Verilog, like primitive. Does iVerilog support that? I have no idea. Does anybody know if Verilog supports primitive? Let's just try to call iVerilog on that and see if it does something. Oh, I didn't throw an error, so that's a good start. Yeah, I mean, it built it. Huh. Okay, interesting. I mean, I still don't think it can work because. Okay, so this one might work because this one actually seems to be wired correctly, right? You have D. You don't have this weird like in the behavioral model here, you have this weird D delayed thing which is comes from nowhere, like some delays in one of the file. Not here. There's this, like the specify thing. I've never, like, I have no idea what specify is. These are like Verilog construct I've never seen in my life before. So I have no idea, yeah, what they are. Dark corners of Verilog, yeah. That, is that like a standard thing or is that like a special thing? Because all the dollar function, they can sometimes be specific to like one specific tool or things like that, right? I mean, I can feed. Is the specify file used by anything? That's a black box with nothing in it. Yeah, okay, that might be the file that you saw with the delay, but that's like an automatically generated test bench, right? All it does is like flip bits at random intervals. Okay, interesting. So you would basically use like the functional model with the specify. Okay, because here if I just do the functional model, I mean, it works. Yeah, iVerilog definitely doesn't like. Yeah, iVerilog doesn't like specify. So I am not sure what tool I would use to even read that. Um, Specify block. What is that to define? Delay across a module. Sound specified is unspecified inside the block. Specified. Oh wait, there's an option to actually. Huh. Okay, so let's see. Maybe my iVerlog version is too old. It's the version I have is probably like the one in the repository, which is. Hmm. Let's see if we can. I mean, iVerlog should be fairly quick to build. I'm really curious if those models are actually usable because I thought they weren't. Oh crap! How do you build iVerlog? What now? Wait. Interesting. Yeah, I've never seen the specify before, but thanks for the information. Oh wait, did I? Yeah, it is. Even the newer iVerlog doesn't seem to like it. So okay, whatever. Anyway, I'll continue on the design and maybe move to the simulation afterwards because oh yeah, it's already been an hour. So let me go back to the diagram. Okay. So that was the right side, obviously. and then you need a read port. So the first thing I thought was just basically take a mux and do like a 64 to 1 mux, and then output registers, and there you go. And then you have your read address 0 and read data 0. Okay, that's like a 1 simple solution for a read port. The problem is like the 64 to 1 mux tend to be very large and very annoying to root. And so something that I wanted to try is basically go 4 by 4. And so by group of 4, I would have a 4 to 1 mux. 3. And then actually a tri-state buffer that drives a shared read bit line, basically. Why kind of this sort of mixed architecture between like a real mux and a buffer is that to drive this line, which might be long and potentially have high capacitance or and still a flip flop, of course, here. Is that I would use like a fairly big drive gate, something like underscore 8 or underscore 16 size gate to be able to drive that line quickly, basically. And it means that this cell is relatively large, and I don't want to have to put 64 of those. And so looking at the area of the various cell and the difficulty of routing, like putting a 4 to 1 mux followed by one of these, I think it's a decent compromise. Of course, I'm kind of discovering all of this, and so I have no idea if the result will be usable or not. I just want to go through the process and simulate the result to see exactly, okay, what did work properly, what didn't, and just get familiar with the tool in general, right? So that's kind of the architecture that I would be looking at. So the cells that are going to be involved are DLXTN, DLXTP. So these are the latch, either positive or negatively enabled. MUX 4 cell. There's a single cell that does a MUX 4. Then you have the tribuff driver, which are called either ebuff or einv, depending if you want a buffer or an inverter. So yeah, I'm not sure which one I will use yet. And then you have the flip-flop here, which is DFXTP. So that's kind of the cells that are going to be involved in this. So now, how can we place and route stuff ourselves? No, not that. Just looking at, okay, that's the one I have. Okay, so that's some stuff that I prepared first. So for experimenting, I wanted like a empty chip with nothing in it. So I quickly wrote a Tcl script that uses OpenRoad to just call the initialized floor plan, and that should have created me like an empty.def, which is just the rows. And so if I open that here, yeah, I have basically an empty chip with nothing in it, with 1 micron surface, but the rows have been defined in it. So kind of where things goes, the rows have been created, and I have 220 rows available. Anyway, but what I wanted to show is called OpenDB, and that's kind of a way to manipulate design and manipulate the DEF and the LEF files. And OpenLANE comes with Python binding for that. So if I start IPython, let me take my notes because I don't know. Okay. So import OpenDB Python as ODB. Okay, and now I can. The first thing I need to do is create a database object. So now I have a database in which I can, load object and do my work. The first thing I need to do is open the technology LEF so that it knows about what technology we're using and the various parameters of that technology, like the layers which are available, the types of vias, and all that kind of stuff. So I want to load them in that DB, and the file is on TNT Sky. Okay, so it learned about all the layers that are available and all the vias that are available in that technology, and it learned some other stuff as well, but it just doesn't display it. Next, I want to load all the cells that are available in that standard library. So I'm gonna read another LEF which describes all the cell. OpenLANE, workspace, PKs, Sky130A, start ref, Sky130 FDHD, SCHD, LEF, Sky130. Okay, so this loaded all the available library, all the standard cells basically available in that thing. Which means like if I want to find one, I can just search for it by name. It's called find master, I think, because it's like the master template, like the master copy of it. Sky130 FD SC Max 41. Yeah, and so I can call up a cell by name. Let me actually use it. Max, right? Next, I want to load my empty file because that's where I'm gonna do kind of my work, like all the tests. Chip ODB dot read. So now I want to load a DF database slash load Sky130 tests floor plan. Okay, so I'm not really sure why, but then I need to go and take the block. I have no idea what's. I haven't actually found a good explanation of all the objects in OpenDB, what they represent, stuff like that. So I kind of learned just from the names. So here I'm not entirely sure what that is, but block is like the main object inside the chip, basically. And here, for instance, you can find, all the rows that are defined where you can place cell. And if you look inside at row 0, for instance, you can see where it is placed and kind of what orientation it has. So, if it's flipped in one direction or another. This one says MX, which is mirrored in the X direction. So it's kind of flipped. Okay, so next step is going to be trying to add a mux to my design. So for that, I have the master copy, which I found by name. I need to create an instance of that. So mux instance equal odb dot create. Inside the blocks, I want to create a copy of the mux cell, and I want to name it mux1. So now I have an instance. Next step is to try to place it somewhere, and I can't. Technically, you can place it anywhere in the design, right? It doesn't have to be aligned with the grid, but the whole point here is to kind of integrate that design as much as possible in the existing grid so that the power and everything is routed nicely, basically. If you try to place it at random location, actually not sure if you're gonna have like DRC error because you conflict, or if it's gonna detect and not route the signals, but then you'd have to route power yourself. It'd be a mess. So just stick to the grid, and it seems like a much better decision. So for that, the first thing to do is to orient the instance correctly. And so I'm just gonna set the orientation. So I'm gonna grab a row. Let's say row equal log.get rows. I'm gonna put it on row 10. It's a random example, right? Next, I want to orient my instance the same way as the row. So what's the row orientation actually? Yeah. me.set orientation row.get orientation. Okay, the next step is to position it somewhere. So if I take the row origin, so xy row get origin, so that's where the row starts. So I have some coordinates. So the y-axis, I can't move it because I would switch to another row, but I can position it anywhere on the x-axis, but you still you have to respect like a given unit of spacing, and that's actually specified in the row as well. Row dot get spacing. So every spacing has to be a multiple of 460. I think it's nanometers. That's in nanometers. So let's just increment the x position by 20, whatever. And then finally, I can set location x, y. So I created my instance, oriented it properly, placed it somewhere on the grid, and next I want to do something that's called placement status. Basically, the object in the database can have different status so that the various step of the process know what's left to do or not. And here, if you look in the spec, there's something called placement status firm, which means that you can't move it. Like nothing is going to move it, not even a placer. And because we want to do the placement manually, that's pretty much what we want, right? And finally, we need to write the results into another file. It's odb.write def block home tnt test floor plan max.df. Really interesting. Oh wait, no, I forgot Sky130. Okay, so in theory, we should have one mux placed on the 10th row on the 20th column. So we can open that in layout. What is something at least? And we do have a cell. So I have no idea if it's the correct row or column because I have no marker whatsoever for them. But actually, I think I can open it in, I think Magic shows the rows. Let me try that. So PDK Sky130A is a tech Magic Sky130A Magic IRC. Okay. DF. No, I need to load the tech LEF first. PDK, Sky130A, libs.ref, FD, SC, HD, tech ADF, and now I can load the. Do I need to read the? Well, I mean, you can't toss them on top of each other, right? Because that kind of will conflict. um, but you usually you want to keep them aligned with the grid, which is why I'm trying to load here. Is to I think Magic shows the grid of the DEF. Sky130 FP. What? Okay. Apparently it doesn't show the row either. Because I have my cell here. But if you look at the input of the placer, that's what the automatic placer does, right? And it's even does that in two steps. Like if you load in, if you look at the floor plan DEF of the first design we looked at the SPM design, all the cells are actually placed at 0, 0. And the first step of the placer is actually distribute them along kind of among the die, if you want, or the area that you defined as, okay, you want that area being used for your cells. And the first step is the global placement, I think it's called, and that's it. It just looks at the connection and doesn't really care about the alignment or that kind of stuff. Cells might even be overlapping and stuff like that, and so it's not a valid placement, but it just gets a general idea of where things should be, and then it runs a second placement step called the detail placer, and the detail placer will move the cell to align them with the grid and make sure that they don't overlap with each other. That's kind of the placement process, and you can actually see that in OpenLANE. If you look at run placement command, which I think is git grep. Yeah, see, you have first step is a global placement, and then later step is detailed placement. I don't know if we can actually see the result of global placement. Does it keep the result somewhere? Maybe. Let me see if I can load it in Kalayout. Right now. OpenLANE workspace, OpenLANE design. Yeah, that's the output of global placement. And as you can see, like cells are overlapping and they're not aligned to the grid, and they're just basically distributed among the chip. I'm not even sure if it's there's an option to be like to have timing driven placement. There's give generation. Yeah, probably. Do you see that somewhere? I mean, I know that. Yeah, here. Um, lot of these process, you can actually ask them to output like the render the placement progressively, so that you can make nice animation and stuff like that. Um, of the of what has happened, and I guess that's it. I've never actually tried it, but yeah. But so yeah, that's the output of global placements. I'm not sure it's timing driven at the moment, so it might just be completely random. I have no idea, or if it at least looked at the netlist and the connectivity. I would hope it at least did that. Um, and then it does the detailed routing where it actually. I'm assuming that's the output. No, that's the same thing. Yeah, open twice the same file. Uh, well, that's actually still invalid. Is it the same? Yeah, so I guess the output is the one that's not in the temporary directory, but in the result directory placement. That's the result detailed placement of this, right? Where it converted every location to something valid. If you give me a second, I'm gonna go grab quickly something to drink because I ran out. I'll be back in a second. So now we know at least how to place a cell. One thing we still don't have is how to actually wire stuff up. And that's not something I know how to do yet, to be honest. I think so. Let's try to actually just add a net or something. Or first, how do you find the pins? That's something I. So if we look at the mux cell and what function we have available on it, there's this thing called get m terms, which I have no idea what m terms stand for, but I'm pretty sure those are the pins. Because you get name, you have A0, and A0 is one of the pin, right? So this would be A0. And so let's try to connect something to A0 actually. So how do we find the coordinate of A0? So what method do I have on that? Get M pins. Okay, so there's one pin defined. Okay, so it's a pin. That's not. Okay, so I can get the bounding box of this, I'm guessing. I'm not super. Huh. So if you look at my understanding is there is actually 8. So the spacing between here and here and here and here. So here is twice the space, so that you actually have a place to run another wire here, and you have one more here and one more here. And so you have 1, 2, 3, 4, 5, 6 kind of spots equidistant to run wires, and then you have the power rails kind of take up a space. I don't know what the distance between this and this. Can I measure? Actually, if I do this, 0.2. Okay. So the total kind of spacing between two tracks is 0.34, and I think that matches the technology file. So if you look at the technology file of, actually I can, it describes sort of what's kind of recommended, and my bad, it's not in the technology file, it's in the track. That defines the routing grid, right? And 0.34 is the recommended spacing between two tracks on metal 1, and that's the one. And so I'm betting that we have twice that spacing here, and so there is actually a spot here to put a track. Now the question is, how do I do that? And how do I know, especially the coordinate of that track? Is it the middle? Do I have the same space here as I do here? 0.54. Yeah, okay. So they're in the middle. They're in the middle. So the x coordinate of my, let's say that I want to make a track that connects A0 and S1. That makes absolutely no sense, right? But I'm just actually, yeah, why not? A0 and S1. So I need the I need to find which M term it is. A1, A3, S0. That's S0. That's the one I wanted to connect, right? No, S1 I wanted to. Well, if I can connect S0, it's fine. So MT0 equal MT1, yeah, MP0. Mpins 0. MP0 dot get geometry. So I need the center x coordinates of this pin and this pin. So I'm just gonna get the geometry x max x min I think, okay, these are functions. Oh wait, does get geometry? What does, wait, what? MP0 dot get? Oh, okay, that returns a list. Okay. So let's go with x0 equal 10, 22, x1 equal 34, 15. Now I need the y coordinate that I want that wire to be at. For that, I can find the row. This, and I want to lower it by half the track space, which is 170. So that would be my y coordinate. Now I need to find how do I make a wire that goes from LI, the local interconnect, through a via to metal 1, from metal 1 there, and then again to And that I'm not sure how to do that. So there's something called an encoder. Okay, so ODB dot so I need to create a net first. Net is ODB dot DB net dot create testnet. Okay, so a net is a logical connection, and then I need to create a wire that's kind of represent, oh, that logical connection is rooted, I think. And so wire is odb.dbnet, no, dbwire dot create that's for that net. Okay, so far so good. Next thing is gonna be trying to route this wire. So you can't add segment directly. You have something called the DB wire encoder. Yeah. Okay. But I need the various layers that are gonna be involved in this. So let me. So in the technology file, the different layers are defined with the name that they're gonna have. So I'm gonna need the layer metal 1. So layer met 1. Did I have a? Huh. What, when I loaded the technology file, how did I name it? TLF. Okay. So in the technology file, I can try to find a layer. Apparently not. Okay. So I can do get tech, find layer metal 1. Okay, so I have the metal layer, and then I need the vias. And so there are several rules for the via depending on which direction things are routed. And so here I think I am along the preferred direction because it's gonna be like a horizontal connection for metal 1 and no direction for things. So I think I need to use that. And so is it find layer? No. Find. So there is find via and find via generate route. I honestly have no idea. Both are defined, and I have no idea what's the difference between them. What's the difference between a via and a via rule? I think one. So the via is just a rectangular area, kind of more static, while the rule seems to try to generate it from what I think I'm just gonna use via. Seems like the simpler option. So did that find? That found something. Okay. So in my encoder, I started that wire. And next, I'm not entirely sure what I need to do. So let's see. So there is actually a test for that. New path. Layer 1. Okay. I'm not sure if I need to start the path at metal 1 or at local interconnect. I'm just gonna start it at layer 1 because that's the only layer I have. I mean, I could get the so encoder dot new path metal layer 1 rooted. X0Y. I'm not entirely sure what's going on there. So I want to add a via right here at this moment. So I'm just gonna do, okay, I'm gonna just try encoder.add via. The question is, should I do add tick via or add via? What's the difference? What's the difference between a tick via and a and a via? Did I do get via or get tick via? Get I just need to find via. Okay, let's just try add via and see what that does. Or not. Okay, add tick via. Okay, apparently it's add tick via. So far so good. And then I want to I mean, what the? Oh wait, you can actually do via dot get. Oh, that's neat. Okay. Interesting. I still have absolutely no idea how. Why does it call new path here? Is it creating something independent, or I I don't understand how this encoder thing works basically. I'm just gonna add another point and then add another via. Okay, let's reload that. Well, it's definitely not any wire where I wanted a wire. Huh. Okay. Let's try to look at the DEF, see if we can see anything in it. So there is a net. So it creates something. But okay, something is very wrong here. Oh wait, yeah. I mean my X coordinates are completely off because I forgot to offset them by the origin of the mux. So wait, my wire is gonna be here. Ah yeah. Here's my wire. Nice. It's completely not where I wanted it, but it's there. Okay. I'm going to manually fix it by adding this to this value, which I should have done in the Python and I completely forgot. And I'm gonna postfix the DEF here because I have no idea how to edit an existing net. So if I do this plus this and this plus this here. Yes, I want to reload it. And now if I look at my cell, hey, look at that. I have a connection between A0 and this. Nice. Okay, so now I want to try to load that in Magic and see if it throws a DRC error at me. Because something is weird, right? Because oh wait, is that just the outline? Why do I have two outlines? Oh, is there like a cell outline? Because the thing is that M contact seems awfully close to the border of A0. And so I'm wondering if that's not a DRC violation, which would be a bummer. So let's try to load that in Magic. Actually, is there a reload option here? Okay, so the good news is that my wire shows up in Magic 2, and I can uh where's my wire? Where did it go? So it definitely sees them as connected. Um, and there is no DRC violation according to this. Which layer is metal 1? That's middle one. I like to hide this layer, but I don't know what it is. Okay, I don't see my layer. Since I did expand, I don't see my my connection anymore. What's going on? Let me restart it. Zwino, do you want to exit Magic and lose it? Yes. Let me restart Magic. Read the technology file. Load the cell. Find the cell. Oh wait, no, something's wrong here. Magic tells me that those two pins are connected using the local interconnect layer. Do we have the same in Magic? Outstanding. Apparently, two tools interpret my file differently. Awesome. I mean, I guess. Well, no, I mean, it says rooted middle one. I mean, I guess it. Huh. So what if I say LI here? Oh, LI1, sorry. I guess it's sort of ambiguous. I guess Magic imagines that, okay, if I start on layer LI1 and then I go through via, I end up at the other layer. And somehow Kalayout interprets it in the other way. Um, yeah, no, Magic sees it as layer 1. Okay, so obviously I'm doing something wrong because Magic and Kalayout don't agree on what's going on. Um, What's more worrying is that Magic wasn't throwing a DRC error, even though I was completely short-circuiting several things in the... No, but I guess it's because I load the LEF and not the full cell. Let me try to load the full cell and see if that helps. So if I do mag left equal mag, so this should have loaded the fully detailed model of the cell and not just the simplified version. And so if I do this expand, no, it's not maglev. Did I misremember? I know there is an environment variable that you can define so that instead of just reading the simplified LEF version, it goes and uses the mag file. Oh, it's mag type, sorry. Okay, so now I have the full details. Here I don't have a DRC error, at least. It doesn't tell me anything. Oh yeah, thank you. Yeah, MacType, yeah. But if I take the other way, I had the error. So if I go back to this, added this, no, and go back here. I mean, here I have a wire in the local interconnect layer that completely intersects with the content of the cell. That should definitely throw a DRC error, right? And it doesn't. I mean, I'm short-circuiting like tons of stuff. The hell? Oh, okay. So yeah, okay. I need to manually force the DRC check, and then it tells me that I have DRC error, which means that in the previous one I didn't have any because I did do a DRC check. Okay. So now I have some confidence between in the DRC results. But obviously I'm doing something wrong here because Well, yeah, because layout and yeah, because layout and magic are interpreting the result differently. They have no idea how. So do I like repeat the point or something like li and then the same point, something like this? Ah, damn it! I always forgot it's li1, even though there is only one local interconnect. But did I save it? Nope. Still puts it in li1. Fuck. How do I get? How do I get both of them to agree on what the thing is? Okay, so I mean, I know more or less how to draw tracks now and vias. The only problem I have is that layout doesn't agree with what's where, which is kind of a problem for me. I maybe if I do this, is that valid at all? Apparently not. Yeah, no, that's not valid at all. Okay, so I have to read more about the nets and how to specify on which layer is what. But I think I'm gonna stop here for now because it's getting late here. So if anybody has any question or anything they want me to address before I cut down the stream, I don't know when the next one is gonna be or what it's gonna be about. I'll try to work out the exact routing, like how to use the OpenDB for creating this particular path, like on my own, just reading documentation or try to find some information in the source code, and start writing like a Python script that actually creates the mux and look into the simulation model. And so I might do another stream on this topic once I'm a little further along to kind of present where I'm at and what works, what doesn't, that kind of stuff. Depending on if people are interested in that or not. Okay, well, if there is no question, I guess not. I hope at least that you were able to follow what I was vaguely doing. I mean, obviously that was just me trying stuff in the code. I know it's not necessarily easy to follow along, but yeah. Thank you for joining, and maybe see you next time. The stream recording will be available on YouTube and Twitch for some time, and you can find me well pretty much everywhere, like on the Slack for SkyWater, on the 1bit and the 1bit squared Discord, um, on IRC, on Freenode in the OpenFPGA channel, or in the SkyWater PDK channel. I'll try to put all the links to those various resources in the description. Okay, that's it. Thank you for joining, and see you next time.